We present our ICCV 2021 paper, Learning to Estimate Hidden Motions with Global Motion Aggregation. Specifically, we propose an approach to explicitly deal with the occlusion problem in optical flow estimation. Here we show two examples of occlusions. In this paper, we extend the definition of occlusion to include any parts of the scene that exist in the first frame but disappear in the second frame. The occluded part on the left is the staff moving behind the bamboos, and on the right is the blade moving out of frame. In optical flow estimation, occlusions are a main challenge due to the lack of matching information. Traditional optical flow algorithms are designed based on the brightness constancy assumption, where the same scene point is assumed to have the same brightness in two frames. We can see that occlusion is a direct violation of such an assumption. Deep learning approaches handle occlusions with a convolution operation. Due to the local nature of convolutions, more significant occlusions still cannot be resolved effectively. Inspired by the recent success of transformer networks, we propose to introduce the attention mechanism to optical flow learning. Existing optical flow networks employ correlation volume to model similarities between the reference frame and the matching frame. We propose to also model self-similarities within the reference frame. Understanding which pixels are semantically similar to the occluded pixels can help infer the motion from non-occluded pixels. Our idea is also inspired by the traditional non-local means approach. In the example on the right, we can see that the point on the right is occluded as it moves out of frame. If we know that it belongs to the blade and is related to the point on the left, which is not occluded, we can use the non-occluded motion to interpolate the occluded motion. Our network is based on a successful raft architecture. The GMA module takes the context features and the motion features as input and outputs the globally aggregated motion features. The aggregated motion features are then concatenated with the motion feature map as well as the context feature map. They are then fed into the GRU module to estimate residual optical flow. To model the self-similarities in the reference frame, we project the context features to a query feature map and a key feature map. We then take the dot product and softmax to compute a 4D attention matrix, which encodes self-similarities in the appearance feature space. We project the motion features encoded from the correlation volume to a value feature map, which is then aggregated with the attention matrix. Each globally aggregated motion feature thus contains an aggregation of all other motion features that are semantically similar. This specifically helps with addressing the occlusion problem. On Syntel clean and final dataset, we have improved over Raft by 13.6% and are state-of-the-art at the time of submission. On Kitty 2015, we perform on par with Raft. We suspect that this is due to the lack of sufficient training data on Kitty, which makes it difficult to learn self-similarities. We show the implicitly learned attention matrices. Note that there is no supervision applied on the attention matrices, and the self-similarities are implicitly learned from the ground truth optical flow supervision. Here we show cases where our approach makes significant improvements. We can see that difficult cases are significantly improved. Here are examples on the Syntel final dataset. We also demonstrate the usefulness of our approach on real-world examples.